Hello. So as I mentioned in the last lecture, which was on positive semi-definite matrices, the next couple of lectures will be devoted to applications for positive semi-definite matrices, because they're extremely important in real life. Okay, so the first application will be to graph Laplacians, which will give us a way to understand how connected a graph is. Okay, so let's just recall what a graph is. A graph is just a collection of nodes and edges. So I'll draw the one from the notes. And an edge is just a pair of vertices or a pair of nodes. So our edges have no direction to them, right? So this edge is the edge 1, 2. This edge is the edge 2, 3. This edge is the edge 2, 4. And this edge is the edge 1, 4. And the way that we notate graphs is we notate them by specifying their vertex set and their edge set, right? So in general, you'll give it as an ordered pair like this. In this case, the vertex set is just the numbers 1 through 4, which recall I use this brackets notation for. And then the edge set is the set containing all of these edges, which I just wrote down, right? That's how you notate a graph. Okay, now for a new definition. So let G be a graph. And let I be a vertex. I be a vertex of G, so a node. Then the degree of I, is the number of edges incident to vertex I. And it is denoted d sub I. Okay, so this is a number that we're going to define for every vertex in the graph. And it's the number of edges incident. Incident just means the number of edges touching that vertex. In other words, it's the number of edges that that vertex is in. So in this example, the degree of vertex 3 is just the number of edges touching vertex 3, so the degree is 3. So in our notation, I would say that D2 equals 3. It has, vertex 2 has degree 3. D3 here is 1. D4 here is 2. D1 here is also 2. So that's the degree of a graph. Okay, and that's a very basic notion for a graph. And what we're going to do is we're going to put them along the diagonals of a matrix. So let's let D sub G, this is going to be an n by n matrix. Right, so our graphs are going to be on n vertices. This is going to be an n by n matrix. Be the diagonal matrix, whose ith diagonal entry is di. All right, so let me just again draw the graph that we had before, 1, 2, 4, 3, with a triangle here and an edge off there. So in this case, the d sub G is just the one where you put in order the degree of the vertices down the diagonal. So it was 2, 3, 1, 2. Okay, recall also the adjacency matrix is the matrix that records the connections between the different nodes, right? So recall the adjacency matrix. I think we saw this both in lecture and in, oh my gosh, adjacency matrix, which I think I can call this A sub G. That's also an n by n matrix, is defined by the ijth entry is 1 if ij is an edge, and 0 if not. Okay, and rather than write the set ij all the time, I'm going to use some slightly briefer notation today. I'll just say ij. Right, so in this thing, I would say this edge is 1, 2, 2, 3, 1, 4, 2, 3. Okay, but of course knowing that every edge is really a set of a pair of vertices. Okay, and now what we're going to do is we're going to define the Laplacian of the graph using these two matrices. It's got a very simple definition. The Laplacian of G is LG equals DG minus AG. So it's almost like the adjacency matrix, except all the numbers are -1 or 0, and the diagonal contains the degrees of the different vertices. Right, so in this example, what is that equal to? So it has the degrees down the diagonal, and then you'll have a -1 in the ijth entry if ij is an edge. Right, so 1, 2 is an edge, also 2, 1 is an edge. That's the same edge. 1 is also connected to 4, so 1, 4 is an edge. 2 is connected to everything, right? It's connected to 3 and 4 as well. And 3 is only connected to, 4 is 4 is connected to 2 and 1, but it's not connected to 3. So I have this matrix here. Okay, so you take the adjacency matrix, you subtract it off of this diagonal matrix. Okay, and it seems like we've just done something kind of random, right? It turns out that this Laplacian will contain a lot of very easily analyzable information about G. Okay, so people who study graphs, they're called graph theorists. Several of my best friends are graph theorists. And graph theorists will generally either study the adjacency matrix of a graph or the Laplacian of a graph. Right? Of course, you can get one from the other, but the Laplacian, it turns out, is a really nice matrix to work with that contains the information about the graph. And one thing that we don't know yet, but we're going to see in 1 second, is that this matrix is always positive semi-definite. Okay, so this is positive semi-definite matrix that contains a tremendous amount of information. I mean, technically, it contains all of the information of the graph, right? Because you can recreate the graph if you just know the Laplacian. But the point is that you can analyze the Laplacian matrix using linear algebra and using the stuff that we talked about for positive semi-definite matrices. And this linear algebraic data contained in the matrix knows an unbelievable amount of information about the graph in a very accessible way somehow. Okay, so here are some facts. I guess let me just list that previous fact again. Some kind of, okay, never mind. Facts. 1, LG is positive semi-definite. We will prove that. 2, lambda equals 0 is always an eigenvalue. Of LG with eigenvector the all ones vector. So the all ones vector is always an eigenvector of every Laplacian, and it corresponds to a 0 eigenvalue. This is actually fairly easy to see, right? So the point is that when we, let me get our favorite example before. 1, 2, -1, 0, -1, -1, 0, -1, -1, -1, -1, -1, 0, 0. Think about how we constructed this matrix, right? What do? We put the degrees along the diagonal, and then the rest of this row represented the different edges that were incident to vertex 1. So it should come as no surprise to you that this row should sum to 0, right? Because we have a -1 for every single edge, but then also for every single edge, we added it up to get the degree. So this diagonal entry counts up the number of -1s there are, and so every row of the Laplacian sums to 0. Every row of LG sums to 0 by construction. So then when you multiply it by the all ones column vector, right? Imagine you were multiplying this by the all ones column vector. What does that do? it just the first entry of the product, when you take the dot product of the first row with that column, all it returns is it just returns the sum of the row, right? So this thing will just be the sum of row 1 down to the sum of row n, which is of course just the 0 vector, because we just noted that each row has to sum to 0 by the way we constructed this matrix. Okay, now let's prove that LG is positive semi-definite. Okay, so there are many characterizations of positive semi-definite, right? Let me just click back to them. Here are all the characterizations of being positive semi-definite. And it turns out that what we're going to do is we're going to show that LG satisfies property 3. We're going to find a matrix B such that LG is equal to B transpose B, meaning that it's positive semi-definite. Okay, so we will show that LG equals B transpose B for some matrix B. Okay, so here's the construction. So define, trying to write neater, define the matrix BG, the directed node edge incidence matrix of G. Okay, so this matrix is going to record the nodes of the graph, the edges of the graph, and whether the nodes touch the edges. And it's going to be directed because some of them will be 1s and some of them will be -1s, but the direction you can actually just choose. So let me tell you what I mean by this. So it's best done by example, of course. So we'll start off with our graph here. And the first thing we'll do is for every edge, we'll just pick a direction, and it's not going to matter which direction we pick. It'll change our matrix BG, but any choice of direction will still give us that LG is that matrix times a transpose. So I'll just pick the direction that is picked in the notes. So we'll make this a directed edge this way, this a directed edge this way. So just add some arrowheads, and it doesn't matter which way you pick. Okay, so now it really makes sense to call this edge 1, 2, because it's no longer a set. It has a direction to it, so I'll list the tail first and then the head. Right, so this is 1, 4, 2, 4, 2, 3. Right, so first pick a direction for each edge. Okay, and then I said that it's the node edge incidence matrix. So the columns of our matrix will represent the different edges, and the rows of our matrix will represent the different nodes. Okay, so we're going to construct this matrix like this. So the columns will be indexed by the edges of G. Okay, so in this case, we have edges. Let me just make sure I'm doing it in the same way as the notes. This one will be 1, 2. This one will be 1, 4. This one will be 2, 3, and this one will be 2, 4. So one column for each edge. The rows will be indexed. Maybe I'll use red. Rows will be indexed by the nodes. All right, so 1, 2, 3, 4. And the way that we're going to fill in this matrix is for each column, in other words, for each edge, I'm going to put a 1 at the start of that edge, the starting node, and a -1 at the ending node. Right, so this edge is the edge 1, 2. So it starts at 1 and it ends at -2, and it has nothing to do with 3 and 4. Right, this edge 1, 4 starts at 1 and ends at 4. This edge 2, 3 starts at 2 and ends at 3. This edge 2, 4 starts at 1 and ends at 4. Right. And I said the direction doesn't matter, so depending on how you chose the directions of your edges, some of you might have called this one negative 1, 1 if you thought that the edge went from 4 to 1. But that's all that's going to change if you choose different edge directions, right? So in other words, in the column indexed by the directed edge, because I'm just choosing a direction for any of them, by the directed edge ij, we put 1 in row I and negative 1 in row j. Okay, in other words, this matrix captures the relationship between the different nodes and the different edges in this graph. Okay, now it turns out that if you take this matrix to be BG, then LG will equal BG times BG transpose. I guess we could do that. Really, you should do it. But I guess let me do that. Our BG was this matrix. 0, 0, minus 1, 0, 0, minus 1, 0, minus 1, times its transpose, right? So this is BG. Its transpose just has its rows equal to the columns of the previous one. What am I doing? Yes, I'm doing this correctly. If we take this product, right, this is BG transpose. Let's see, the first row dotted with the first column, you get 2. The first row dotted with the second column, you get minus 1. First row dotted with the third column, you get 0. First row dotted with the fourth column, you get minus 1. Second row dotted with the first column, you get negative 1. Then you will get 1 plus 1 plus 1. In other words, you get 3. Then you'll get negative 1 again. Then you'll get negative 1 again. Then you just do this process. I have the answer here, of course, but you should check for yourself. And this thing was exactly our graph Laplacian LG, right? It captured the degrees of the vertices along the diagonal, and then it had minus 1s representing the different edges between the different nodes. And now, why did this really work, right? So let's think about this. Remember that the rows of BG are indexed by the nodes, right? Each row tells you some information about the nodes of each row tells you something about the connections of that node. And that row tells you all of the edges that BG is going to be incident to. Sorry, that node is going to be incident to, right? So this one was like says that it was incident to 1, 2. This one said that it was incident to 1, 4. Now, the columns of BG transpose are exactly the same thing as the rows of BG. So if you dot the first row with the first column, all of the edges that first node touches, you either have a 1 or a minus 1, but you multiply it by itself. So you get 1 for every edge that node 1 is incident to, and you'll get zeros everywhere else. In other words, it just counts up the number of nodes, of edges that node 1 is incident to. So this is true along every diagonal. The second row in the second column, third row in the third column, fourth row in the fourth column. Right, so if you take the ith row and the ith column, you'll just get either 1 squared or minus 1 squared for every edge incident to I. So you'll get, so the sum is just the degree of I, which is what it's supposed to be in the Laplacian. Okay, what about for the non-diagonal entries? Well, then for the non-diagonal entries, remember that this this column was the second row of BG. This represents the second node, right? This one was the first node. And exactly the fact that 1, 2 is an edge means that wherever that edge is, in this case it's the first column of the matrix, you'll get a 1 in BG and a -1 in BG transpose, or you'll get a -1 in BG and a 1 in BG transpose, right? One of them will be 1 and one of them will be -1 when they share that edge. Every other entry, right? This was the edge 1, 4. So 1 will have a 1 there, and 4 will have a -1 there, but 2 will have a 0 there because 2 had nothing to do with that edge. So if you dot the ith row with the jth column, you'll get a 1 in one of them and a -1 in one of them at the point where they share that edge. So the product will be -1. Right? So in the ith row and the jth column, if I is not equal to j, if ij is an edge, you will get one of them to be 1 and one of them to be -1. You'll get -1, and everywhere else, you'll get 0. If ij is not an edge, you're going to get a 0 there too, right? So in other words, in the ith row and the ith column, you get the degrees, along the diagonal you get the degrees. Every other ij, you get -1 if there was an edge between I and j. You get a 0 if not, and that's exactly the definition of the Laplacian. It's the degrees along the diagonal and -1s representing all the edges. Okay, so that's a sort of a hand-wavy proof, but hopefully you can kind of see why from this example. Which means that the Laplacian is positive semi-definite. Which means that we know quite a bit about its eigenvalues. Its eigenvalues are all non-negative. So let's state this as its own result, because it's a very important result. So if G is a graph, the Laplacian LG, L sub G, not the brand, is positive semi-definite, and its eigenvalues are, so we know that 0 is an eigenvalue. That's one of the first things we said. And then we know that since it's positive semi-definite, all of the eigenvalues are non-negative. Since it's symmetric, all of the eigenvalues are real. And so we can say this, not only that, we even know that we have an eigenvector with eigenvalue 0, the all ones vector. And 1 is an eigenvector of LG with eigenvalue 0. Okay. So nothing actually new here. All I'm doing is I'm just combining these two facts, that it's positive semi-definite and 0 is an eigenvector with eigenvalue 1, and what we already know about positive semi-definite matrices, namely that they have non-negative eigenvalues. And it's just convention. Okay, it's one possible convention is to label the eigenvalues in order, with the smallest one being lambda 1 and the largest one being lambda n. Another convention is to do the opposite, but generally you want to adopt some convention that tells you something nice about your eigenvalues. The size of them is as good a one as any. And we know that since LG is positive semi-definite, that means that its quadratic form is always non-negative, right? Since LG is positive semi-definite, the quadratic form is greater than or equal to 0 for all x and Rn. And it turns out that we can actually understand it explicitly for the Laplacian. Here's the proposition. Okay, so let G be the following graph, right? So be the graph with vertices, the integers from 1 through n, and edges e. Edge set, really. Okay, so if x is this vector of n variables, then it turns out that this quadratic form spits out the following thing: the sum over all I, j, and e, xi minus xj squared. Sorry. Okay, so it takes your variables and it looks at every edge in the graph, and if ij is an edge, you have a term of xi minus xj squared. So this is explicitly what the quadratic form associated to a graph Laplacian is. And notice that from this description, it's very clear that this is going to be non-negative because it's a bunch of square things added together. So why? Well, let's prove it. Right, so we know that LG is equal to BG transpose, where BG was the directed node edge incidence matrix. Right, so this means that X transpose LGX is the same thing as X transpose BG transpose X. Right, so let's understand X transpose BG. Let's understand X transpose BG. Okay, now if we look at what we'll do here is we're going to take the row vector x1 through xn, and we're going to multiply it by the matrix BG. But remember that each column of BG represents an edge, right? So the columns are indexed by edges. This will be some ij. Well, what happens in the ijth column? So ij is an edge of your graph, because that's how I constructed BG. And you'll have a 1 where the edge starts, and a -1 where the edge ends. Right? So in this product, the columns of BG were indexed by the edges of G. So the rows of this product will be indexed by the columns, so by the edges of G. Right? This one is 1 by n. This one is n by k, where k is the number of edges of your graph, and so this one will be 1 by k. It's indexed by the edges of your graph, and it will exactly have xi minus xj at the row indexed by ij. Right, so if this first column was in our example, it was like the edge 1, 2, then this will have exactly x1 minus x2. The next one was the row, the edge indexed 1, 4. So next one will be exactly x1 minus x4. Okay, so this means in the end, what our column vector is going to be, this X transpose BG, every single entry will be non-zero, and it will be xi minus xj, where I and j form an edge of G. So the entries of X transpose BG, are all going to be xi minus xj, where ij is an edge of G. And you'll get every single edge represented. Okay, so what does that mean? Well, notice that this thing is the transpose of this thing. Right? This thing here is X transpose BG transpose, which means that this is just the dot product of XTBG with itself, right? So this is just this vector dotted with itself, right? So X transpose LG X is equal to this vector XTBG dotted with itself. And when you dot the vector by itself, what you do is you square all the entries and you add them all up. This is the sum over all xi minus xj squared, where I and j is an edge, which is exactly what we want to show. Okay, so you should do this in the example. In other words, you should take x1, x2, x3, x4, and then we take our, let's just actually take the edge node incidence matrix. That was this one, right? Where we recorded all of the edges in the columns, like this. What happens when we take this dot product, right? So this one is x transpose, this one is bg. We get exactly x1 minus x2. That's the top entry, x1 minus x2. The next entry will be x1 minus x4. Next one will be x2 minus x3. Last one will be x2 minus x4, right? Just by the way we constructed it. And of course, now if you take x transpose bg, bg transpose x, you'll just get the dot product of this with itself, which is exactly this sum of squares where the terms are given by xi minus xj, where I, j are edges in the graph. Okay, and of course here, if you chose a different ordering, if you chose a different direction for each edge, you would get like x2 minus x1 instead of x1 minus x2. But x2 minus x1 squared is the same thing as x1 minus x2 squared. A squared is the same thing as negative a squared, right? Okay, so now that we've set up all this work with the graph Laplacian, let me tell you one of the major uses of the graph Laplacian. Okay, it turns out that the graph Laplacian can tell whether or not your graph is connected. So let me just state what connected means. So a graph G is called connected if there is a way to walk from any vertex to any other vertex along the edges of G. Okay, so we're going to see in a second that we're going to look at this example where you have edges here and you have edges here, but no edges between them. This is an example of a non-connected or disconnected graph on 6 vertices, right? Because you can't get from vertex 1 to vertex 4 by walking along edges. Okay, and of course, whether or not a graph is connected is a very basic property of the graph, right? So there's some examples given in the notes. One is maybe you have a road network inside of a city where you represent each road with a vertex, and you put an edge between 2 roads if those roads intersect, right? So you draw this huge graph with roads and edges if those roads intersect. What does connectivity mean? Well, you can think of the edges then, right? So if there were 6 roads and they were connected like this, road 1 intersected road 2, that means that you can drive from road 1 to road 2 because they intersect. So if your graph is not connected, it means there's some roads that you can't get to from some other roads, right? So the connectivity of this graph really tells you how connected is your road network. Can you get from every road to every other road? Same thing, we could look at all the graph of all of the friends on Facebook, right? So you put every user on Facebook as a node, you put an edge between them with their friends. Asking, is the graph connected, is the same thing as saying, can I get from any user to any other user through a sequence of acquaintances, right? It's like 6 degrees of Kevin Bacon or whatever, right? Like I'm friends with John, who's friends with Cindy, who's friends with Jason, who's friends with whoever. Can I get to anybody by just a sequence of acquaintances? So there are many situations in which you want to know whether a graph is connected or not. You could also ask more subtle questions like, how connected is the graph? How easy is it to get from one vertex to another? Right? That's a subtle question. But one thing is that the Laplacian, in particular the second eigenvalue of the Laplacian, tells you whether or not the graph is connected. So if you have a humongous graph, right? Really imagine the graph of Facebook users, right? There's like 100 million nodes, and there's some edges between, there's all kinds of edges between all kinds of people. But how do you tell whether or not you can actually get from one person to any other person? If you just drew the graph, you wouldn't be able to look and tell. But you can use linear algebra to tell, because it all depends on the second eigenvalue of the graph Laplacian. Okay, so here's the theorem. G is connected if and only if the second eigenvalue is positive. Okay, remember, I'm sticking with this convention all throughout. So the first eigenvalue is 0, and then all of the eigenvalues I'm listing in increasing order, strictly increasing order. And so whether or not the graph is connected just depends on whether there's any other 0 eigenvalue or there's not. If there is another 0 eigenvalue, then the graph is not connected. If the next eigenvalue is actually positive, then the graph is connected. Okay, and one direction of this proof is actually not so hard to see. Okay, so the point is that if G is not connected, for example, this e.g. above, then if you think about what the graph Laplacian looks like, the graph Laplacian will look something like this. You can break it up into blocks. So what you do is you just list all of the vertices in the first component, so 1, 2, and 3 in our example here, and all the vertices in the second component, or however many components there are. You just list them all together, right? Then all of the edges in the graph live entirely in this quadrant and in this quadrant. In other words, you'll have zeros here because there are no edges between 1, 2, and 3, and 4, 5, and 6. Okay, this is at least up to reordering of the vertices, but reordering the vertices is not going to change the properties of the graph Laplacian. You can actually prove that because, how do you prove that? You can prove that if you multiply by a permutation matrix, then the determinant only changes up to a sign, and so the roots of the determinant don't change. Because the permutation matrix, right, sorry, we already saw this. We saw this in a homework exercise. If you do row operations on a matrix, then it doesn't change the determinant except up to a sign, which means that the characteristic polynomial only changes up to a sign. So if you have a not connected graph, you can do this by just rearranging, and it's not going to change the eigenvalues of the Laplacian. Okay, but then once you know that it looks like this, you can find two different eigenvectors with eigenvalue 0. Namely, you take just ones in the first component or ones in the second component. So these are both eigenvectors with eigenvalue 0. So if your graph is not connected, you can break the graph Laplacian into two pieces, into two blocks, and you can find an eigenvector for each of those blocks. That says that the geometric multiplicity of the eigenvalue 0 is more than 1, which means that the second eigenvalue is 0, right? Okay, and this idea works in general if G is not connected, but let me just hand wave my way a little bit around it and just say that you could just identify any component that's disconnected from the rest, right? There might be more than two components, right? But you just take any one of those disconnecting components and shove them all up in the upper left of your matrix, take all the rest and put it in the bottom right, and then there's no connections between these vertices and any of these vertices, so you'll get 0 along these blocks, and you'll be able to find 2 eigenvectors like this. You can actually find more than 2 eigenvectors. You'll get an eigenvector for every connected component, right? In other words, actually, if you look at more of the eigen values, it can tell you how many connected components there are, right? But for one thing, definitely, if it's disconnected, the second eigenvalue will be 0. So that's one direction, right? So we sort of proved that if G is not connected, then lambda 2 will equal 0. And actually, if G has k components, k connected components, then lambda 1, lambda 2, up to lambda k will actually all be 0. Now we should show the converse, right? By the way, a more full explanation is written in the notes, but hopefully this discussion in the lecture helps you understand that well-written discussion in the notes. Okay, so if I think of this theorem as an if and only if statement like this, we show that if G is not connected, then lambda 2 is not greater than 0. In other words, we showed the contrapositive of this direction. That's what we've done so far. I still need to do this direction. In other words, I need to show that if G is connected, then lambda 2 is positive. Okay, so we still need to show that if G is connected, that the second smallest eigenvalue is positive. Now, note that we know that since LG is a symmetric matrix, that it has n different eigenvalues, and we know that the geometric multiplicity is sum to n. So it's enough to show that the geometric multiplicity of 0 is actually equal to 1. Because if the geometric multiplicity, because for a symmetric matrix, the geometric multiplicity always equals the algebraic multiplicity, right? So for a symmetric matrix, we know that it's diagonalizable. AM lambda equals GM lambda for all eigenvalues. So we just need to show that the geometric multiplicity of 0 is equal to 1. If the geometric multiplicity is equal to 1, it means the algebraic multiplicity is equal to 1, which means that 0 only occurs as an eigenvalue once. And since all of the eigenvalues are non-negative, that means the next eigenvalue needs to be bigger than 0. Now, how do we show that the geometric multiplicity of 0 is 1? Let's let U be any eigenvector with eigenvalues 0. Okay, so since it's an eigenvector with eigenvalue 0, that means that LG times U is equal to the 0 vector, or 0 times U, which is the 0 vector. So that means that 0 is equal to U transpose LG U. Right? Because if you multiply by U transpose times the 0 vector, you'll get the number 0. But this thing was also supposed to be, if you take all of the edges in G, Ui minus Uj squared. Okay? However, each of these summands is non-negative, so if they all add up to 0, this means that every single term has to be 0. Hence, Ui minus Uj squared equals 0 for all edges Ij in E. Okay, now, since G is connected, I can walk from any vertex to any other vertex. I can walk from vertex 1 to any vertex I want. Now, along the edges of G, right? So if U1 is equal to C, so I'm looking at the first term in my eigenvector, then every other vertex that 1 connects to also has to have a value of C, right? So if V1 equals C and 1k is an edge, then also UK has to equal C. Right? Basically, every edge, every vertex that's connected to 1 has to have the same value as 1. But then, for every edge connected to K, for every other vertex connected to K, it also has to have value of C. In other words, what this is saying is that whenever you move from one vertex to another along an edge, the value of U1, so let's say 1, 2 is an edge, that would mean the value of U1 and U2 have to be the same, because as you walk along that edge, you see U1, you see U2, the difference needs to be 0. Right, so similarly, if Kj is an edge, then now Uj has to also equal C, because Kj will appear as an edge. What does this say? This says that as you walk along the graph, every vertex you can reach has to have a C in this eigenvector. But the graph is connected, which means that you can walk from 1 to every single edge. So you can walk from 1 to every single node, which means that in this eigenvector U, all the entries need to be 1. Right, so since G is connected, this implies that my vector U is just the all ones vector. Sorry, it's C times the all ones vector. It could be a scalar multiple. What does that mean? That means that I have a one-dimensional space of eigenvectors. Every eigenvector is just a scalar multiple of the all ones vector. So this means that the algebraic multiplicity of the eigenvalue 0 is just 1, which is exactly what I wanted. Okay? So if you are connected, oh, by the way, this also would show now, if you consider just the different connected components, the same argument you start at any edge will show that you can have 1s everywhere in that component, 0s everywhere else, that thing will be an eigenvector with eigenvalue 0. And so the number of 0 eigenvalues tells you exactly how many connected components your graph has. Right? So slight generalization. It really follows from what we did, but you need to maybe permute the labelings, so it's a little annoying, but the number of times that 0 is an eigenvalue of LG counts the number of connected components of G, which is a very interesting thing to know, right? So this is one example where a matrix that you very naturally arises from something that you care about. You care about a graph. You very naturally get the Laplacian matrix, which is a positive semi-definite matrix. And then knowing stuff about positive semi-definite matrices lets you know a lot of stuff about the graph Laplacian. And we already have a very clear application. If you want to know how connected your graph is, you look at the smallest eigenvalues of L. Okay, in fact, not only does it tell you whether or not the graph is connected, it tells you, if it is connected, it tells you how connected it is. Sort of in general, the larger, right? So if the second eigenvalue is 0, you're not connected. If it's anything above 0, you are connected. It turns out that the larger the second eigenvalue is, the more connected your graph is, in a really precise sense. Okay, so also a fact. Okay, so the second eigenvalue Lambda 2 is called the spectral gap because it's the gap away from 0. It's also called the Friedler value of the Fiedler value of the graph. And as I just said, this Fiedler value or the spectral gap tells you how connected your graph is, and we'll see a little bit about what I mean by that in the next lecture. All right, see you then.